Okay, so we can see how we can calculate this average in an incremental way. Okay, the standard way, let's say, which is inefficient in terms of time and memory, is to simply keep in memory all the rewards that you get as you apply n actions, and then you just recompute the average. Okay, but there is a better way to do that, which is an incremental way, and this is the formula we saw in the algorithm. So the next q will be the previous q or the current q plus 1 over n, where n is the number of iteration, and this will be multiplied by the subtraction of the reward that you get in iteration n minus the q value for that action in that time. So this is the standard form, and you have seen this rule in learning, in other supervised learning methods, and sometimes it also appears in some unsupervised learning methods. And this is the idea of that the new estimate will be the old estimate plus some portion of some measure of error, which in this case the error will be defined like the target value minus the old estimate. So how we can get to this rule? So we have the average of some rewards. This can be represented as 1 over n of the sum from 1 to n of the rewards, and this sum here can be expressed as the reward in time step n plus the sum of the previous rewards from 1 to n minus 1. Now here we apply a trick. We multiply this by 1, but this 1 will be written as n minus 1 over n minus 1. So this is 1, so we don't change anything important. But it is a good trick, because then introducing this 1 over n minus 1 will allow us to write this as qn. Okay, so qn will be the average of all the previous n minus 1 rewards. And once we have this expression, we multiply n by q and minus 1 times qn. We have this expression, and finally we move out of this expression the n times qn. We move it out, and then the n will just cancel out, and we will have qn, and the remaining expression then will be plus 1 over n times the other two terms, rn and minus qn. And that's how you create the incremental learning rule for the average. Now this way to calculate the q values, like the average of the rewards, is very good if you are working with a stationary problem. As in the first case, we assuming that the machine is not changing internally the reward distributions, and it has been proven that if that alpha, the alpha that we see here, this step size, we call it alpha, if that step size is if you sum all the alphas from 1 to infinity, if it gives you infinity, and if you sum the square of those alphas and you get something less than infinity, then these two are conditions that will assure you that eventually you will learn the right or the true Q values. So these two are mathematical conditions to assure you that the algorithm is going to converge, and the estimation of the Q values are going to be the right ones, the true ones. So 1 over n is hold true to these two properties or conditions. So 1 over n is a good idea for alpha, for step size, but for example 1 over n squared is not, or does not guarantee that this, especially this one, is not going to hold true for this selection of alpha. And remember here, this n is the number of times that you execute the action A. So these conditions are true. I mean, this is a mathematical proof that this is true. And this is in the case of stationary problems. Okay. In general, you can apply this for stationary problems with p in the interval, this interval 0, 1, where we have this n minus p. So this is 1 over n to this exponent, which should be between 0 and 1. If you select your alpha to be in this interval, with this p in this interval, then this is going to be true and your algorithm is going to converge. Okay, and this is the big O complexity of that, which is 1 over the square root of n. Now this is true for stationary problems. However, there are two drawbacks with this idea. Is that first one is that yes, this is true, you will allow your algorithm to converge, but this is going to happen with many iterations. So this process is very slow if you work with this alpha. So in practical terms, you don't use this. You, instead of using this as a function of the number of execution of the actions, we prefer to have a constant alpha. We will talk about that in a moment. So this is the first drawback. This is very slow. And the second drawback is that this is true only for stationary problems. And most of the reinforcement learning problems are non-stationary. So for non-stationary problems, we need a constant alpha, because let's say the distribution of the rewards are going to be changing, and we don't want our algorithm to converge, or we would like to converge, but that is not possible at all, because the distributions are going to change all the time. So we need to be changing the importance that we give to each of the rewards. As you remember, this expression here comes from the average of the rewards. In the sample average, what we are doing is giving the same importance to any of these rewards. And this is not good for non-stationary problems, because suppose that n is, let's say, 10,000. You are already executing 10,000 times some action. In a non-stationary problem, after executing some 1,000 times the action, it is highly probable that the distribution rewards had already changed, and it doesn't make sense to give the same weight to the very first reward that it was given 10,000 time episodes before, at least, than giving the same weight to a recently obtained reward. So this is not good for non-stationary. So what we want to do is to give more importance or more weight to the rewards that we are having more recently in the current time, and give less weight to those rewards back in the past. In this way, we can adapt faster to changes in the reward distributions of the environment. And the way you do that is by using a constant alpha. So suppose the true action values change slowly over time, then this is the case of a problem that is non-stationary. In this case, sample average, as I explained, are not good idea. Why? Because of the concept I have explained, that we need to apply different weights to the rewards depending if they happened recently or back in the past, because that's way we are going to approximate or get closer to the real reward distributions. And one way to give these different weights is to apply this exponential recency weighted average as opposed to the sample average. And one way to do that is consider this expression here, where the Q value for an action in time step n plus 1 will be defined as this expression, where you will have here 1 minus alpha to this exponent, which is n times q1, where this q1 is the initial q value. Remember that you need to initialize the q values for every action. This is the initial q value, plus the sum of 1 from 1 to n, okay, of this product here, alpha times 1 minus alpha to the n minus I. So this expression, this is times the reward. So what is the idea behind this expression here? Suppose that you have already executed 1000 actions, but you want to give a weight to the reward that you obtained in the very first execution of the action. So we are in time step 1000, but we are going to give a weight to the first action. So I equals 1. So n is 1000, I is 1. 1000 minus 1 is 999, and this is the exponent for this power here, 1 minus alpha. Remember that alpha should be in this interval 0, 1. So if you have here a decimal number and you apply some exponent, if the exponent is large, since this number is decimal, the result is going to be a smaller number. So as you increase the exponent, the result is smaller, and as you decrease the exponent, the result is larger. So a reward that was generated or obtained in time step 1 will have a very small value or weight if we are now in iteration n. But in the other extreme, suppose that you are given a weight to the most recently obtained reward. So we are in time step 1000 and we are calculating the weight of the action executed in time 1000. So 1000 minus 1000, that's 0, and this to the 0, any number to the 0 is 1. So you are going to consider alpha times of the reward. Okay, so this expression is called the recency weighted average, and the idea is that you will reduce the importance of the rewards exponentially as you go back to the past. Now this first part of the expression is also important to analyze. Here we see that the initial value of Q is some value that we will assign in the previous slides we said, okay, let's initialize them like to be 0. The Q is going to be 0 for every action when we start because we don't have any information. That is important and will create a bias in the learning process, as we will see now. For example, suppose that in our machine experiment, if you remember, we said that the mean of the rewards for every action will be 1 with some variance. It will be around 0 with variance 1. So if you initialize, instead of initializing the Q values with 0, you initialize them with 5. That is highly optimistic because we know that those actions will give you rewards around 0 more or less. So saying that you will have a 5, it's highly optimistic. What happens if you do that? As I said, this first value is going to bias your learning, and what happens, as you can see in the results of these experiments, this black curve, in these black curves, all the actions were initialized with Q values to be 5, and what happens is that as you start executing actions, you will see that the actual reward that you will get will be less than 5. And in the learning rule, let me go back, you need to subtract from the reward what is the current expected Q value. So if you initialize this to be 5 and you get, let's say 1, you will get 1 minus 5, and then the Q value that you initialized as 5 will be reduced. Okay, so the next time that you select an action, you won't select that action because it has already reduced the Q value. So you will execute any other action, but not that one. If you select a second action, the same is going to happen. You will have a reward that is less than 5, and as a consequence of that, the Q value for that second action will be reduced to. So what you're doing is that you are exploring more, because all the actions, you will be disappointed with every one of the actions that you perform because they will give you less than 5, and you will end up trying all the actions in order to maximize the Q value, and that has a positive consequence because you will explore more. So initially you will gain less rewards than the standard or a realistic initialization of the Q values. You will have less reward, but since you will be exploring like exhaustively, you will faster learn or discover which action is the optimal one, and then you will stick to that action most of the time, and then you will increase the rewards, and in this case this is the number of times that you execute the optimal action. So if you are working with a stationary problem, then it makes sense to start with optimistic values of Q. Okay, but once you have started running, then since this is you only start learning one time, only in the beginning you can apply this trick, of course, because it is the initialization. The impact is not that good in the long term. And remember, this is the case of a stationary problem in which we can play this trick. If we are facing a non-stationary problem, then it doesn't make sense to do this, because as we know, the distribution of rewards is going to change sooner than later. So This is a trick that can work with very simple problems, and it has an impact only in the beginning. But it is good to analyze what happens with the initial values of Q. Okay, there is a different way to select the greedy action. So far we have selected actions following the epsilon greedy strategy. But as I said before, you can define many ways to select actions. This is another way. This is called upper confidence bound. And the idea behind this strategy is that when you select a random action, you select a random action with, let's say, with a uniform probability. So you can select an action that is very, very bad, or you can randomly select an action that is very close to the optimal one, let's say. Epsilon greedy cannot make a difference, cannot detect this. What we're saying in this algorithm, UCB, is that we need to consider how certain we are about the expectation of some action. And as we increase the times that we repeat an action, we will be more certain about the real reward that we can get from that action, as opposed to an action that has been executed very few times. Our expectation is not that precise, that certain. So there's a lot of uncertainty. So this concept of be certain about the execution of the reward that you will get for an action is considered in this term here. So to select the greedy action, you will select the action that has a maximum in this expression, and the expression will contain two terms. The first term is just the current Q value, but you have a second term that is the certainty about that prediction. So we have here this constant C. In this experiment they applied C equals 2, but this term is how much value you are going to give to this number here, this factor. And this factor here is the square root of the logarithm of t, the natural logarithm of t, over the number of times that action A has been executed so far. So if we analyze this, first t is the time step, okay, the iteration of the algorithm, the current iteration time. So when you apply the logarithm, you are telling that the time will be bounded by a logarithm, and remember the logarithm has this shape more or less like this blue curve, so it doesn't grow like exponentially or constantly, but it is bounded. So as you increase the number of times that you have played with the Bandit machine, this numerator is going to be larger, but is going to be bounded because of the logarithm. So this larger number will create a larger factor, and that will increase the certainty about any of the actions. So as you increase the number of iterations, you will have more certainty about the expected reward for every actions, which makes sense. After playing many times with the machine, then you are more certain about how good or bad each of the actions are. And this is about the numerator. And if you increase in the denominator, as you increase the number of times that you execute a specific action, the denominator will increase for that specific action, and increasing the denominator will reduce the result of this square root. So you will decrease the certainty about that action. Okay, so this is a way to a different way to select the greedy action. And in this experiment, you see that it is slightly better if you use this UCB algorithm instead of using the epsilon gradient. There is another way to select actions. This is called gradient bandit algorithm. This is called gradient bandit because this is derived using the concept of ascent gradient. Here, this strategy, we consider this big H, which is what is the preference that you have to select a specific action. So it is a preference measure. We need to keep track of a preference value for each of the actions, and this preference is used in the softmax probability function in this way. So here this B is just an index over each of the possible actions, k actions. This denominator is just for normalization, and here we have the exponential to this power, where the exponent is the preference for the action. So this expression will give you a probability for each of the actions, and then you will execute the action with the largest probability most of the time. So that's the idea. And how we can define this preference value? The way you do it is with this formula, where you have, after you have executed A one more time, you will update the preference for that action to be the current preference value plus some portion alpha of this subtraction, the reward that you just got with that action, minus this reward bar, which this reward bar represents the average of rewards that you have obtained with all of the actions that you have executed so far. So this is a way to compare the reward that you got with this action with the reward that you have received, the average of the rewards that you have obtained during the whole training time. So the idea here is to consider the relative benefit of executing some action according to the average of the rewards. So if the reward that you obtain is larger than the average, you will say that that's a good action. Then this will be a positive number, and then you will increase the preference over that action. But if the reward that this action gave you is smaller than the average of the reward, then you will say, okay, this is not a very good action. This subtraction will be negative, and then you will reduce the preference over that action. And here is just to consider the current probability is going to be 1 minus pi, and this is again this function that will give you 1 when you have that the action that you are evaluating now, this A, is the action that was selected in time t. So they run experiments with this idea of gradient bandit algorithms. By the way, this is the definition of the reward, the average rewards. It's just you sum all the rewards and you divide it by the number of times that you have executed actions in that problem. And well, they run experiments using this expression. The blue result is when they considered this average reward. This is what they say with baseline. This average is considered a baseline, and the brown curve was performed or was obtained without baseline. So what they did is simply say, let's consider that this average is just 0, so we ignore this baseline. And you can see from these experiments that it is better to consider this baseline, this average of the rewards, to compute this relative preference over some actions. So this is another way to perform action selection. So here are the final comparison among the 4 kinds of action selections that we have studied. The first one is epsilon greedy in red. The other one is gradient bandit, is the one that we just reviewed. And here this black is with an optimistic initialization. And remember that this works only with stationary problems. So you can get a good boost if you initialize optimistically the Q values. And here is with the UCB algorithm. Now, even though this gradient bandit, UCB, and initialization performed better than epsilon greedy, the main problems of UCB and gradient bandit versus the epsilon greedy is that these are very difficult to implement in more complex algorithms for more realistic reinforcement learning problems. So that's why, even though in these experiments you see that UCB and gradient bandit is better than epsilon greedy, in the real applications of reinforcement learning, we usually always prefer to follow some epsilon greedy strategy. And in the case of this optimistic initialization, we saw that this works only with stationary problems, and most of the time we are solving non-stationary problems. Okay, so these are all simple methods, but they are complicated enough, and we will build on them. So the next algorithms that we are going to study are based on these ideas of computing averages and handling this exploration-exploitation trade-off with epsilon greedy. So it is very important to understand these very basic ideas and concepts behind the bandit problem. There are other open questions that we will need to solve, like this idea of handling the input information and how we can better select actions in a sequence of the decision making problem. So these are questions that we will try to answer later on. And yeah, so this is an algorithm that learns from evaluative feedback as opposed to supervised or supervision, like in supervised learning. This is mainly evaluative, and we need a way to balance this exploration and exploitation, since we are learning from evaluations, from some reward feedback. And the very important thing about these algorithms is that in the end what we want to do is to maximize the reward in the long term. And the only way that we have to perform this maximization is by trial and error. So we need to interact with the environment, executing actions, and learning from the rewards that we are obtaining. So we always want to maximize the reward. So okay guys, thank you. I hope this is useful, and talk to you later. Bye.